This talk is by Giulia Semeghini from Harvard, and she'll talk about exploring topological phases in Rydberg atom arrays.
Okay,
so it's 30 minutes plus 15.
Yes. Awesome. Okay, thank you very much for having me here. This is not my typical conference, and so this talk will be quite different from everything else that you will hear in these days. So my goal here will be to introduce you to this platform, which is a programmable quantum simulator, as we like to call it, that is based on Rydberg atom arrays. And I will show you some of the experiments that we have already done to explore topological phases in this context, but my main purpose here would be to stimulate discussions and so that you can understand the platform well enough that we can see what we can do in these experiments that tries to answer some of the questions that are relevant to this community. So if I'm going too fast and I'm not explaining things, please interrupt me at any time. So let me first tell you a little bit about the platform. So this platform based on programmable Rydberg arrays is one of the most recent quantum platforms out there. So it's about 7 years old. So we can consider it to be the kid among the quantum platforms out there. But I would say our claim is that it's a pretty smart kid that in only 7 years have already become quite competitive to these other older quantum platforms out there. So what are the core ingredients of this platform? So the quantum building blocks are neutral atoms. And the reason we want to use neutral atoms is because they can be very well isolated from the environment, which is crucial for these quantum machines. And we can manipulate and read them out with very high fidelities. And we want to use them in a specific setting where we have individual control. So we use these so-called optical tweezers to trap individual atoms one at a time. And also we can read them out individually. So we have site resolved readout. And I will talk about this in a second. And we combine this with the ability to engineer strong interactions between the atoms using Rydberg excitations. And again, I will tell you something about this in a few slides. So the goal here is to generate a programmable quantum platform that has applications in many different fields within quantum science, which are quantum simulation, quantum information processing, and also metrology. So the things that I'm going to talk about today are mainly related to these first two. So what we can do in terms of study of topological phases that is relevant in these two, for these two directions. So let me start with showing you how does the platform look like. So we start from these two-dimensional arrays of optical tweezers, where optical tweezers are simply these tightly focused laser beams that can trap single atoms inside of them. And so what you see up here is an image of this two-dimensional array of tweezers that is taken in their focus. So you see you have these tight traps. So now when we shine these arrays of tweezers on a cold cloud of atoms, what happens is that we start loading the atoms in a stochastic way into these traps. So each spot that you see up here corresponds to a single atom. And so we have about 50% of the traps that are filled with an atom and the rest is empty. So now, of course, if we want to do anything useful with this, we would like to create an ordered array. So the question here is, can we deterministically fill a subset of these traps? So to do that, we use a second set of tweezers that are movable. So here the colors are not helping me a lot, but we have a second tweezer here that is superimposed with this one. And we can use this to catch that atom and move them across the array so that we can shuffle the atoms to the array to create something that is ordered now. And so after this sorting procedure, we get something as what you see here on the right. So we have 600 traps here in total, and we can fill these 300 traps on the left with pretty high fidelities. So let me just show you a few different experimental repetitions where you see that this typically works pretty well. And we have an average of 99% filling of the target traps in this left corner. So the nice thing about this procedure is also that it's very flexible. And so we can arrange the atoms into different geometries. And here are just a few examples. And here you can immediately see that this is very convenient because depending on the type of phenomenon that we want to study, you can easily change the geometry. As a matter of fact, what we do in the lab is just change a few lines of code. We don't need to touch anything on the table. And so in a few minutes, we can get from a square lattice to a Kagome and so on. Now, of course, if you have tools like this, you can have some fun and create these nice videos of vintage video games using the atoms. Okay, so first thing, we have these two-dimensional arrays of atoms with the first level of programmability, which is the geometry. But now we have these arrays where the atoms sit a few microns apart. So being these neutral atoms, they don't naturally interact with each other. So what we do is the following. We start with the atoms in an electronic ground state, and then we use an optical transition to excite them to a so-called Rydberg state. And the Rydberg state is simply a highly excited electronic state. So we have principal quantum numbers between 40 and 100, more or less. So what happens here is that you have this electron that is sitting out there on this high orbital. So it's far apart from the nucleus, which means that the effective size of the atom is about 1,000 times larger than what it is in the ground state. So you have a strong dipole here. So if you have two atoms that are both in the Rydberg state, what happens is that you have strong van der Waals interactions between them. And these, on the order of a few microns, are of the orders of tens of megahertz to gigahertz. So you can have interaction times of the orders of fractions of microseconds. So now if we consider a pair of atoms at a certain distance r from each other, you see that when we have this optical transition on, we can excite one or both of the atoms to the Rydberg state. But now if you put the atoms closer to each other, because you have these van der Waals interactions, then the energy of the doubly excited state is shifted up. And so exciting both atoms to the Rydberg state is not energetically allowed anymore. So this is a phenomenon that is known as Rydberg blockade, which simply tells you that within a certain distance, you can only have one Rydberg excitation at a time. And this characteristic distance is provided by this blockade radius. Okay, so now we have two-dimensional arrays of atoms with programmable geometry, and we can also introduce strong interactions using this Rydberg blockade. Now that we have more or less all the relevant ingredients in mind, we can look at how we can use this platform to achieve this goal. So one first thing that I want to show you is, I keep talking about this as a programmable quantum platform. You've seen some of the elements of this programmability already, but let's look into this a little bit further. So the general goal that we have in quantum science is to produce some kind of interesting, highly entangled state. And using this platform, you can do this in two different ways. The first one is the analog approach, where what you do is you try to engineer the Hamiltonian of your many-body system. So you try to tune the different parameters that you have in the system, such that that Hamiltonian encodes an interesting many-body state in its ground state or in some excited state, or you can study some quantum dynamics that is determined by the Hamiltonian. But the other approach is to use a digital approach, which is what we typically have in mind when we think about a quantum computer. So you realize a quantum circuit that is a sequence of gates that can generate, for example, a desired entangled state. There is actually a third way that is combining these two, and so realizing a hybrid approach where you use both analog and digital dynamics. And I will give you a quick example about this at the very end of the talk. So let me first show you a little bit how these two work in this specific platform. So let's look at an example of how we can use this analog quantum dynamics. So the simplest example is to look at a square lattice. So we have this two-dimensional array where the atoms sit on a square lattice. And when we have this optical transition for all the atoms that is turned on, now we have the ground state that is coupled to a specific Rydberg state that we choose, and we can consider this as a two-level system where the ground state is our spin down and the Rydberg state is our spin up. So when the atoms are coupled to the Rydberg state, we also have these van der Waals interactions. So the Hamiltonian that describes the system is this so-called Rydberg Hamiltonian, where we have a drive term where sigma x is simply the operator that couples G to R at a site I of the lattice, and this is proportional to the Rabi frequency of the optical transition. Then we have a detuning term where Ni is the occupation of the Rydberg state at a site I of the lattice, and delta is the detuning of the optical transition from the Rydberg state. And finally, we have the van der Waals interactions between atoms in the Rydberg states. So this is actually, this corresponds to an Ising Hamiltonian with a transverse filter. Now, if we consider the specific situation where the blockade radius looks like this, so remember what I told you before, this means that if you have an atom in the Rydberg state there at the center, its 4 nearest neighbors are all blockaded, so they cannot be simultaneously excited to the Rydberg state. And now we can look at what are the many-body ground states of the Hamiltonian as a function of this term delta that we can tune in the experiment. So if we go to large negative detunings, we have this trivial ground state where all the atoms are in the ground state, right? We don't have enough energy to excite to the Rydberg state, so you have this trivial many-body state. But if you go in the opposite direction, so for large detunings, what happens is this term is negative, so to minimize the energy, you would like to maximize the number of atoms in the Rydberg state, but you have this constraint that comes from the Rydberg blockade, and so at most, you can excite half of the atoms to the Rydberg state. And so the Rydberg excitations form this checkerboard pattern that you can see here, which correspond to the antiferromagnetic state, where neighboring spins are anti-aligned with each other. And you see that this is the state that matches this Rydberg blockade constraint. Okay, so how do we, so this is a snapshot that we took in the lab where you see this is these are actual experimental data. So we do a state preparation that I will describe in a second, and we look at the final result. And here you see the red circles correspond to the atoms in the Rydberg state, and you can see that every once in a while we get a perfect antiferromagnetic state. So how do we prepare this? This is a nice example of what analog quantum dynamics means in this case. We do a quasi-adiabatic state preparation, which means the following. So this is the state preparation that we implement. We turn on omega, so we turn on the lasers that realize the optical transition, and we start with a negative detuning at the beginning. So we start in this state that is very easy to initialize for us. And then we slowly tune the parameter delta, the detuning of the optical transition, such that we slowly change the Hamiltonian from this situation to this one, such that the system, if you do this slowly enough, should just follow in the instantaneous ground state of the Hamiltonian. So this is a nice way to connect the trivial ground state that you can prepare at the beginning to the final, more interesting ground state that you want to study. Okay, so here you see what these analog quantum dynamics mean. We have an Hamiltonian that we can tune, and we just do a continuous change of the variables here to prepare a state of interest. Now let's look at the opposite regime where we do digital quantum dynamics. What are the fundamental tools here? So first of all, how would we define our qubit? So in this case, we don't use the Rydberg state as a qubit state, but we use 2 hyperfine states of the electronic ground state. Why do we use these 2? Because this type of qubit has long coherence times, more than a second. It has high fidelity manipulation and readout that have been studied for many, many years. And the atoms in this state are non-interacting, which can be useful, as we will see in a second. So what we do here is we define these as our 2 qubit states, but then we only excite to the Rydberg state temporarily for fractions of microseconds to switch on the interactions. So we switch on the interactions, we entangle the atoms, and then we always go back to these 2 hyperfine states. So then what we want to do in typical quantum algorithms is to implement entangling gates. And so here I won't go at all in the details, it would take too much. But the general idea is you have your 2-dimensional array, you shine the atoms with this Rydberg laser drive. And so what happens is that if the atoms are within a blockade radius from each other, they will get entangled. We apply specific pulses of Rydberg lasers that I won't describe here, and so the atoms become entangled. And so the idea here is that you have these global Rydberg pulses, all the atoms are illuminated with these Rydberg lasers, but only the atoms that are within a blockade radius of each other will get entangled with this specific pulse sequence. And the nice thing here is that if you want to change the connectivity, you just move the atoms around using the tweezers. So you see here, I'm going between 2 different configurations. You change the connectivity, and so in a second entangling gate, the atoms that will become entangled are different pairs from the initial ones. And you will see in a few slides how this can be used to create some very interesting states. Okay, so now that we have hopefully a good understanding of what these two modes of operation means, let me show you two examples. So here we finally get to topology. Sorry, it took a while. But I'm going to show you two experiments where we realized the same type of topological phase, which is a Z2 quantum spin liquid. In the first case, using an analog type of quantum dynamics, and in the second case, we implement a Toric code, we generate a Toric code state using this type of digital approach. Okay, so let's start from the analog example. So here we want to realize a quantum spin liquid. I don't have to explain to you what a quantum spin liquid is, but let me just go through the initial idea of Anderson of a quantum spin liquid so that I can introduce the analogies that we use in our case. So as you well know, he was considering the spin 1/2 particles with antiferromagnetic interactions on a frustrated lattice. And so his idea was that in this configuration, what the spins would do was to form entangled pairs, also called dimers, that correspond to the superposition of up-down and down-up. So all the spins in the system would pair up in these dimers. And so being that all possible couplings between the spins have the same exact energy, then the many-body ground state would simply be the macroscopic superposition of all these possible dimer configurations, which is the very well-known resonating valence bond state. So the question here is, can we realize something like this using our Rydberg atoms? And let me show you how this analogy works. So using Rydberg atom arrays, we can create something that looks like these dimer models. So let's take this triangular lattice, but in our case, we put our spin degrees of freedom not on the vertices of the triangular lattice, but at the center of the bonds. So we do this for all the atoms in this way. Now let's say that we have a Rydberg excitation here on the red atom is a Rydberg excitation. Now, if we have a certain blockade radius, it means that the next Rydberg excitations need to be outside of this radius. So this is what we get. And now let's say that we map each Rydberg excitation to a dimer that connects the two adjacent vertices of the triangular lattice. This is just a mapping. These are not actual dimers. They correspond to a single atom. But let's do this mapping. What you see is that the dimer configuration here on the right is exactly identical to what you have in the left, meaning that the blockade radius gives you some spatial constraints on the Rydberg excitations that is the same that you have for the dimers here on the left. So this idea originally came from two different groups at Harvard. I see Ashwin is in the audience. So from Subir's group and Ashwin's group, there was this idea that we could create these analog dimer models using Rydberg atom arrays. The geometries they study here are not this triangular geometry. That doesn't really work very well. But in the experiment that I will show you today, we will look at this second model from Ashwin's group, where we can study topological phases using this idea. So let me show you how this works in a bit more details. So the geometry that we use in this case is a Kagome lattice, where again, we have a Kagome lattice where the atoms are sitting on the links, not on the vertices. Now, if you choose the blockade radius in a proper way, you get into this configuration where if you have a Rydberg excitation here, its 6 near zeros are all blockaded. And this allows you to map this configuration for the Rydberg excitations to a dimer model of the Kagome lattice. So you see that if you have maximum filling allowed by the blockade mechanism, you have that all the vertices of the Kagome lattice belong exactly to one dimer at a time. And this corresponds to a certain filling fraction that is 1/4. Now, what was studied in this theoretical paper from Ashwin's group is that there exists a range of parameters where there is a quantum spin liquid state that again corresponds to the superposition of all the possible dimer coverings of this lattice. So what we do in the experiment is exactly the same as I showed you before for the square lattice. Now we are in a more intricate geometry, but it's exactly the same. So we perform this quasi-adiabatic state preparation. And this is an example of a snapshot that we take at the end of this state preparation. So here the atoms in the Rydberg state are marked with these red dimers according to this mapping. And you can immediately see a couple of things. So this is a pretty good dimer covering of the lattice. You see that most vertices belong to a single dimer. We have a few missing dimers here and there. And the second thing is that you cannot detect any obvious spatial ordering, which is what you would expect for a spin liquid. Now, how do we actually know if this is the quantum spin liquid phase that we wanted to prepare? The nice thing about this platform is that we can measure topological string operators. So you are probably familiar with this if you know about the Toric code. This is exactly the same thing that one measures in the Toric code. So these are strings of single particle operators. And again, as I was mentioning, this is the key advantage of this platform in this type of studies, because we have access to this microscopic information. We can take a snapshot, look at the state of each individual atom, and reconstruct these string operators. So here, unfortunately, I don't really have time to go into the details of these measurements. That would be very interesting. But let me just show you in one slide what we do here. So we want to verify that this is the state we're preparing. So we want to do two things. The first one is identify if the state we're preparing is a dimer state. And second, check that it's not just a single dimer state, but it's actually a superposition of all these different dimer configurations. So we want to check that we have this coherent superposition, which is the trickiest part here. So to do these two things, we measure two different string operators. So for the first measurement here, we measure this diagonal string operator Z, which simply measures the parity of dimers along a string. So here we look at this closed loop. Every time we cross a dimer, we get a -1. Every time we cross an empty bond, we get a +1. And so these closed loop operators have a very well-defined expectation value only when you are in a dimer state. So the expectation value should be -1 to the number of vertices enclosed by the loop. If you are in a different state, if the filling fraction is not exactly 1/4, as I was showing before, these on average will always give you 0, because at each different snapshot, you will get something different. So we measure this in the experiment, and what we see is that there is a range of the tunings, which are our tuning parameter, where we do indeed observe a finite expectation value for these string operators. Then we want to measure coherence, and so for this we measure this second string operator X. Again, not too much time to go in the details here. Actually, the experimental details here are very interesting. But what we want to do here is measure basically the coefficients of this superposition, or some of them, let's say. So again, I'm not going to tell you how we do this, but we do measure these X operators, and again, we see that we have this range of parameters where these expectation values also finite. Again, if you're interested afterwards, I can tell you a little bit more about this. So here, by measuring these two, we have access to this microscopic information that tells us that the state we're preparing is indeed compatible with a quantum spin liquid. Now that we have this quantum spin liquid, what we can do is also use it to create a topological qubit. So what we want to do here is generate an array with non-trivial topology. So something like a donut, but in 2D. So this is just an array where we carve out a hole in the middle. If you add this hole in the middle, you now have topological protection that is given by this topological phase. So in particular, in this case, what this topological protection means is that your dimer states are now separated into two distinct topological sectors, such that if you have local perturbations, you will always remain within the same topological sector, and to go from one to the other topological sector, you need to do some non-local, non-trivial transformation. So now we can define the spin liquids that live in one or the other topological sectors as our qubit states, 0 and 1. And we can also define logical operators for these qubits. Now we can measure this in the experiments, and we see that in the region where we identified our quantum spin liquid, the state that we naturally prepare is the plus state for the topological qubits, so the symmetric superposition of the 0 and 1 states. So again, here I'm going very fast, and I'd be happy to give you more details afterwards if you're interested. But this is just to show you that using this spin liquid that we can generate by engineering this Hamiltonian in the system, we can also do the first steps towards the realization of a topological qubit that is based on this Z2 spin liquid. Now, of course, we would like to do more. And so the next steps would be to learn how to encode and manipulate these qubits. And this requires, learning how to define and apply these logical operators, which implies manipulating abelian anyons, and in particular, realizing braiding operations. The second thing we would like to do is engineer the boundaries of the array to generate and study non-abelian anyons that can be created at the intersection of E and M boundaries. And we have some ideas on how to do fusion experiments to study the statistics of these non-abelian anyons. And finally, since this is not a self-correcting topological state, we would like to use error correction on this topological phase to see how we can create better topological states and use them for quantum information purposes. Okay, so let me go to the second experiment, where we now use a digital approach to create a toric code state. And so let me assume here that you're all fairly familiar with the toric code. So here's the graph state that we would like to implement. And what we do in the experiment is to add a few ancilla qubits that we use to mediate entanglement between the data qubits here in black. So how does this work? I showed you before that we can move the atoms around while preserving coherence. So what we do here is the following. Let's say that we want to create entanglement between these four black qubits here, the data qubits. We move the ancilla qubit next to this first qubit here. We perform an entangling gate. Then we move it again next to the second here on the right, second entangling gate, and so on and so forth for all the four qubits, so that at the end we have created entanglement between the four qubits mediated by the ancilla qubit in the center. And the nice thing here is that since we can move the atoms around through the array, we can actually create an effective three-dimensional torus, because we can, even if the atoms are in 2D, we can close the boundary conditions on both in both directions, and so create an effective three-dimensional torus. And so let me show you how this works in the experiment. Here are our atoms. We identify some of them as our data qubits in black here, and we have 8 ancilla qubits in red. So at the beginning, we have these 8 pairs that we get entangled in the first layers of qubits, and then we start moving them around. So then we have a second entanglement gate, a third, a fourth, and then we move the ancilla atoms up so that we can perform some selective operations on these two groups of atoms. So this is just a movie to show you how we can combine atom transport with local entangling gates to actually create non-local entanglement through this array of atoms. So of course now we can characterize the state we prepared to verify that we prepared a toric code state. So we can measure the stabilizers, and we can also measure the expectation values for the logical operators to check that we did prepare a specific state of the toric code. The nice thing here is that being in 3D, we actually are encoding 2 different logical qubits, right? So this is different from the first example where we only had 1. Now we have 2. And so here again, what I wanted to show you is how we can use these tools that I introduced you today to efficiently realize, for example, in this case, a quantum error correcting code that is efficiently realized thanks to this highly parallel optical control that we have in this type of experiment. Okay, now let me give you a few ideas of things that we could do in the future. So what are other topological phases that we could study with this platform? And then I'd be very happy to hear if you guys have more ideas. So for example, can we realize non-abelian topological phases? And so we've heard before about this Kitaev honeycomb model, and there was a proposal that you can find on the archive that was put up there in October, I think, where it was proposed a way to realize a Kitaev honeycomb model using, again, Rydberg atoms. Now, this is very tricky because you have these anisotropic interactions that are not very easy to engineer on this platform. So the proposal here is to use Floquet engineering, so using a periodic drive where the frequency of the drive is faster than all other energy scales in the systems to realize an effective static Hamiltonian, and combine this with this atom transport that we just talked about to change the connectivity between different layers of these quantum operations. So the idea would be the following. You have the atoms in this honeycomb structure. You put atoms on the X links close to each other, and you apply this HX Hamiltonian. Then you move them again to put the atoms on the Y links close to each other. You apply this part of the Hamiltonian. Then you move them again. You apply the HC part of the Hamiltonian. And you do this many, many times with a high frequency, such that this is the driving Hamiltonian that you're applying, and the effective Hamiltonian corresponds to the Kitaev honeycomb model Hamiltonian plus these terms that break the time reverse of symmetry. So again, I'm not going into the details, but you can look at this paper to see how they propose to realize the phase, to perform state preparation, characterize the phase, and also perform some braiding experiments to check the statistics of the Abelian topological phase. So now let me do some self-advertisement. So I'm starting my own group at Harvard that now is still an atom array, but with 2 atomic species. And the advantage of the atomic species in this context of studying topological phases is that using the 2 atomic species, you have more interaction terms that you can play with. So you have a possibility to do Hamiltonian engineering in a more flexible way. And also you have this nice possibility of doing non-destructive readout that could be useful for the measurements of some observables. And so let me just mention 2 ideas that we've been looking into. One is to realize trimer states that have Z3 topological order. There are some proposals out there, but it seems that with the 2 atomic species, there are some interesting regimes where this can be studied more efficiently. And then there is this second idea that is very recent and very rough, that is to study a 2-dimensional pyrochloride lattice, where the use of the 2 atomic species would allow us to create the right type of connectivity that you need on this lattice. Okay, with this, let me conclude. Let me thank, these are the people that were involved in the experiments that I mentioned today. So you have the experimental team up here and this large group of theory collaborators that we always benefit from and that were protagonists of many of the ideas that you saw today. So with this, let me thank you, and I'm happy to take any questions.
So, thank you for a very nice talk. Are there any questions?
Thank you. This is really fascinating. I have a question about the experimental data that you showed. So sometimes it was shaded, the region where you say there is a quantum spin liquid, but in the data there is no very sharp kinks. So what I was trying to understand is whether the limiting factor is finite size or whether it's decoherence.
Okay, good question. So yeah, sorry, I went very fast on this. So the idea here is, okay, of course you would expect, if this is a perfect spin liquid, first of all, you would expect this expectation value to go up to 1 and -1 for all these loops, which is not the case. So let me comment on this observable, which is easier to think about. Here, let's see, if we look at the previous slide here, so of course you have these expectation values of +1 and -1 when you have a perfect dimer covering. Of course, if you look, for example, in this case, every time you have a defect here, the expectation value just flips on the opposite side. So this observable is very unforgiving in a sense. It completely changes when you have a single defect. So the fact that the expectation values are smaller than 1 is just because it's an imperfect dimer covering, for example, in this case, and same in this case, the coherence is not exactly perfect in this case as well. The limiting factors are both things you mentioned. So of course we have a finite size lattice. So near the boundaries, of course you don't have a spin liquid phase because you have some, the excitations here on the boundaries are more localized than they would be in the bulk. But I would say when we look just in the bulk, the limiting factor are the coherence effects that you have in the system. And so we're actually working on the experiment to upgrade some of the laser excitations and some of these details to make these decoherence effects less important. And so we would hopefully find something more interesting soon. What you see here is that, of course, this expectation value is decreasing with the size of the loop, which means that, in a sense, you can understand this as a spin liquid which has a finite correlation length. So you have small spin liquid fractions, but you don't have correlation lengths that extend through the whole array. Yeah, that's how we think about this.
Do you know of any way to make a three-dimensional system, like maybe by using multiple different atom types?
Yes. Okay. So it depends on what you want to do. So in a sense, what I showed you in the second experiment is that just by using this atom transport, in a sense, you can even if the atoms are in 2D, you can create a connectivity that is effectively 3D. But on the in experiments of the first kind, where you have a Hamiltonian that describes a system that is not realized in this way, you could, in principle, have an actual 3D array, and this has been actually shown a few years back with these tweezer arrays. It's a very complicated experiment, and so I think nobody is really planning on doing any serious experiments in that regime. I think what would be fairly easy to realize is an experiment where you have only a few layers, let's say 2 to 3. That is still fairly simple to do. Having a full 3D array is kind of difficult in this type of experiments because the optical controls becomes very complicated. But it's in principle possible. I think so far we also don't have very strong motivations. Most of the things we want to do are in 2D. But if there's anything very interesting to do in 3D, we could talk about it. Yes.
Thanks. This was a very nice talk. So I was wondering, so all of the stuff that you showed has to do with density, or in some sense, spin density interactions. Mm-hmm. Have you thought about how you could possibly couple to the momentum rather than the position, in the sense that, for example, if you put your array on a ring or a kind of Corbino disk geometry and move the tweezers around the ring, would that simulate a sort of vector potential? And then you could get access to all the...
Are you thinking of a geometry where you move the tweezers during your, quantum operations? Are you thinking about something like that?
Yeah, essentially like giving a Lorentz boost. Looking at the system in a moving reference frame in a disk geometry that would be equivalent to moving your tweezers continuously around the disk.
Yeah, so I think there would be two approaches to have any coupling to the momentum degree of freedom. One is if the atoms could actually tunnel between different traps, which is not the case now. There are people that are working into pushing this into that regime. So the tweezers here are typically too far away from each other, and so tunneling is basically suppressed. There are people working into that direction. What you're talking about, that is moving the tweezers, I think it's in principle possible. I think the question is, can we do this fast enough with respect to the other timescales in the system? Potentially, it's not very easy, but I think Potentially, I think it's a possibility. It's not been done yet, for sure.
I think a more interesting possibility would be if you could do it slow enough, as in that would correspond to doing something adiabatic.
Well, it depends slow and fast with respect to what, right? So your slow might be still very fast in terms of, you know, how fast you can move these tweezers. But maybe we could talk about what would be the actual timescales that one would need. I think it's in principle possible. There are some technical challenges, but I think it's in principle a possibility, yes.
Okay, thank you.
You're welcome.
I guess the system looks very useful for quantum simulations. How big, what's the roadmap here in terms of the size of these processors?
Yeah,
and you know, what is, I mean, we sort of know the other, you know, the leading technologies like the ion traps and also the Josephson devices, there seem to be, you know, natural limits to how big the systems can be. So what do you think is the limiting factor here?
Yeah, that's
and
very good question.
how big will it get?
Yeah, so of course, at a first glance, the first big advantage of this platform is scalability. So it's much easier to scale up the number of qubits than any other platform out there at the moment. So right now, the experiments that we've done so far are in the few hundreds of qubit range. Mm-hmm. So for example, the speed liquid experiment had 220 or something like that. We just, a few months back, we saw the first arrays with 1,000 atoms. So we're getting there, and I think getting to 1,000 or a few thousand atoms is achievable with the same exact experimental techniques that we're using here. We're already thinking about how to go beyond that. If you want to go to, let's say, 100,000 up to 1 million, then you really need to change the way you're doing things. And so we are thinking about it, meaning you have limitations that just come from optics, basically.
Yeah, I mean, that's the next question, obviously. How big how much real estate is occupied per atom at the end?
Yeah, so basically the limitations you have here are like your microscope objective that you use to image the atoms, laser power, how you can, so the idea would be, for example, to combine arrays coming from different lasers so that you can, in a sense, increase the total power. But also you need to think about different ways of imaging the system, which can host a few, like, let's say 100,000 atoms. So these are things that we are actively thinking about. I think a hard limit would be, I don't think you can go, well, I don't think you can go beyond 1 million atoms in one system. So at that point, you also need to connect, let's say, through photonic.
But you didn't ask, so the footprint for each qubit right now, for each atom is microns, is that correct?
Yeah.
How much? So several microns.
A few microns. So you can squeeze the tweezers close, I would say, to, like, the closest we've done so far is like a couple microns.
Mm-hmm. Okay, thanks.
Yeah, thank you.
Yeah, I have actually a few questions. Maybe the first one is just something I didn't quite understand. So in order to realize the RVB state from, say, on the Kagome, so I understood how you create just one configuration of dimers. So are you just cycling through all the different configurations by moving the atoms? And if yes, then is the fact that this is limited in time, it's limited by the size of your system?
So what we're doing here, we're claiming, I would say, is that every time you do this state preparation, the system is in a superposition of all of these. And so when you measure, you're projecting into one of these states, but before measuring, you have this coherent superposition of many. So the way you then measure the system is to repeat this state preparation and measurement many, many times. So every time you take a snapshot, you will see something different.
So here you didn't prepare these guys by using I forget how you call it, digital thing?
No. This is analog. So here we have the Rydberg Hamiltonian. Let me go back to that slide. So here you have this Rydberg Hamiltonian. You do this state preparation that I mentioned. So you're trying to initialize the system in the ground state of this Hamiltonian. So that's what you do. In the second case, then you have this Toric code realized using quantum gates, but in this case, no. You just let the Hamiltonian, generate the desired topological state, yeah.
And the other question I guess I had is the Rydberg blockade thing. It's not an exponential decay, it's a power law?
It's 1 over r to the 6. Where do you have it?
So you're claiming that it's good enough to really separate when you have your circle?
Yeah, so if you look at how it decays, it's fast enough that then outside of the blockade radius, the interactions are very small. But actually, there are some details that Ashwin can talk to you about. These interactions beyond the blockade radius actually matter more than we would expect, that we were expecting in the beginning. So there are some details that come from those beyond blockade interactions. But yeah, most of the times they don't. In this case particularly, they kind of do.
And just maybe one, I'm sorry, I'm using my advantage here, but the bigger, when you were showing these bigger radii, when you had more atoms, I guess, then the difference between, whether you're inside your radius or outside your radius, right?
I'm not sure. Are you talking about when we measure the string operators, or?
Well, I think anytime, like when you were also showing about how to generate this, you had lots of atoms.
Like in these arrays here?
Probably this one, yes, indeed. And so then, the R 1 over 6 is, the decrease is higher when you're smaller to the.
Yeah.
So
yeah, but all you need to create these superpositions is that, on this short range that is the blockade, you don't allow multiple excitations, such that the frustration that you have in the system generates this big degeneracy in the ground state. Yeah, so that's the idea.
Okay. Thank you very much. I think we should go to the coffee break and see you after that.